I'm going to be going through the second set of slides that I have, also adopted from the MIT Introduction to Deep Learning course, which was taught by Dr. Ava Amini. So I'm going to be covering the overall topic of sequence modeling, and more specifically, how we can use a type of deep learning called recurrent neural networks in order to perform these sequence modeling tasks. So first, I'd like to start with a hands-on example. So let's say we have this white ball in a 2D environment, and I want you to predict where it will go next. However, with all of this information where you just have the ball, it can be confusing. Where will the ball go, as you have no previous information on its motion and no possible idea where it will go next, so most likely your guess will be completely random. However, if you are provided some previous history about where the ball is coming from, you will be able to tell that the ball is going to go right, as its previous motion was moving from left to right. So this is the idea of sequential data, which represents parts of data at time step by time step, so that way we can train models on this time step like data, so that way it can generate new sequential data or possibly classify the sequential data. So there are many different examples of sequences in the wild. Even just me talking to you right now, the audio of me speaking can be broken down into individual sounds that are considered sequential data. And there is much more, such as videos, stock prices, motion, medical readings, biological sequences, weather data, and much, much more. So sequence modeling is especially useful as much of the data we work with in real life is sequential. So there are different applications of sequence modeling. So previously we only had one-to-one classifications. So for example, with binary classification, where we examined the question of, will I pass a class, yes or no, which was a binary output of 0 or 1. But now with sequence modeling, we can add many different modalities. So for example, if we want to have a long sequence turned into one output or classification, we can perform sentiment classification tasks, where we can take a sequence of text and determine if it is positive or negative or any possible emotion. Additionally, we can take a single sequence and turn it into much more. So that will allow us to, for example, generate image captions. So if we provide an example of an image, then we will allow a model to say that what the image contains, such as a baseball player throwing a ball. Additionally, we can now map many sequences to many sequences for things like deep learning translation, where you have a given text and you want to turn it into a text in a different language, such as the transition between English to Mandarin. So there are so many different applications of sequence modeling beside this, making it such a powerful tool for us to use in machine learning. So first, I'd like to introduce the idea of neurons that have recurrence by going back to what we covered previously. So we have the perceptron that has a single computation based on inputs and their weights, and then that computation is put through a nonlinear activation function to achieve an output. Additionally, we saw how we can combine these perceptrons to create a hidden layer with multiple neurons that maps inputs to outputs in multiple dimensions. So let's take this diagram and simplify it to a single matrix of inputs sent through a sort of black box that is green of all of the computations of our hidden layer to give us a matrix of an output yt. So now let's just simply flip this horizontal representation to be vertical. And if we want to take it to handle sequential data, we can use it to handle each individual time step of the data. So let's say we have a 3-character sequence of text, so we can take this input to output mapping and use it 3 times. However, sequences often have order, and the order especially matters in text. So we want to make sure that the previous inputs are taken into account when processing a output for the new input. So let's say we want to see what output we will get for our last input of x2 for the output y2. We will need to take into account the previous inputs of x0 and x1 as well as their outputs. So to do this, we introduce neurons that have recurrence. We do this by taking this state of our hidden layer, which is called the hidden state, and passing it between each neuron, so that way we can have each hidden state understand its previous state. So this is mapped, for example, for this x1 to y1 mapping by taking an input of x1 as well as the previous step of h0, which is the past memory. So this will allow us to get our output of y1, taking into account both the previous states as well as the input that it is currently at for a given time step. So we can simplify this extended diagram into a single recurrent cell that loops back in itself, which is why recurrent neural networks are recurrent. So now I'd like to cover more in-depth examples of recurrent neural networks, as well as more in-depth understanding of how they work. So to have a recurrent neural network, we use our previous example where we take an input and our previous state and put them through a function to compute the weights for our current state at a given time step. So for every time step in a given input data, each time step will have its own hidden state, and each time step's hidden state will contribute to the next. So this is called a recurrence relation between each time step. So let's say we want to implement this in some arbitrary code. Let's say we have a recurrent neural network object called RNN, and we have a hidden state initialized as a list of 4 zeros. And we have a sentence of I love recurrent neural, so now we need to predict the next word. So for each word in our given sentence, we're going to run the recurrent neural network on each word and the hidden state that it is currently at to get our new hidden state as well as a prediction for the next word. When this loop is done and we are at the last word, neural, we will get the next word prediction, which will be networks. So if our RNN is trained correctly, we will be able to take the input of I with our current hidden state of all zeros to get the prediction of the next word, love, as well as update the hidden state to account for that word I. Then do the same for love, recurrent, and neural, continuously updating the hidden state to have different values based on its previous memory in order to get our prediction based on that context. So now that we have our recurrent neural network update, we can look at an input vector of xt, which will be a given matrix, update our hidden state for a given time step by taking into account that input as well as the previous hidden state and putting that calculation through a activation function such as hyperbolic tangent, and then getting an output by multiplying the output weights by the hidden state. So overall, we have a input vector, we multiply it by its associated weights, and add that multiplication to the weights of the previous hidden state, multiplied by that previous hidden state, and sum them together and put that through our activation function of hyperbolic tangent, and take our new updated hidden state to get our output vector by multiplying it with the weights for that output vector. So this now allows us to have a computational graph across different time steps where each input will have its own hidden state with the weights that is passed with, and then each time step will have its own output based on the weights between the hidden state and that output. And for each time step, we can compute a loss value. So for the input x0, we can get L of 0. For input x1, we can get L1, and so on for as many different inputs as we have. Then we can sum all of these losses to get our final loss value for the recurrent neural network. We'll be using this diagram later in order to see how we can optimize this neural network. So we also need to remember that we need to reuse the same weight matrices for every time step. So between the input and the hidden state, all of the weights for each time step should be the same, and the same goes for the weights between the hidden state and the output. So now let's implement an example recurrent neural network with TensorFlow. So we create a class called myRNNCell based on the built-in TensorFlow layer, and we give it weights for the input to the hidden state, the weights for the hidden state, as well as the weights for the output. We give each of these weights the correct dimensions, so that way the recurrent neural network will work and all of the multiplication computational operations will be correct. Then we can initialize our hidden state as all zeros for a given shape of all of the recurrent neural network units for each time step. Then we can implement our mathematical operations in code using a call function where we multiply our current hidden state by its weights and sum that with the current input with its weights, and then use the tanh hyperbolic tangent activation function in order to operate it on this sum and give us our new hidden state. Then we can get our output by multiplying that new hidden state with the weights for the output and returning the new hidden state as well as the output to continuously update it for each time step. So since this recurrent neural network architecture is so commonly implemented, we can use built-in layers in TensorFlow and PyTorch, so that way we don't have to create this complex class every time we want to use it. So in TensorFlow, this is the tf.keras.layers.simpleRNN, which we define by giving it a given number of time steps that we want to have. Similarly, in PyTorch, we can use the torch.nn.rnn and give it an input and output size. So I see in the chat that we have some messages of questions. So we have the difference between continuous and sequential. So continuous data is when all of the data is represented as one vector, whereas sequential data is where it is broken down into individual steps. So for example, if we have a sentence of "I love recurrent neural networks," continuous data would be the entire sentence, whereas sequential data would be looking at each individual word inside the sentence as each one is individual, so it has time steps. So with recurrent neural networks, we can now use this architecture for our previous binary classification with the normal neural network, as well as all of our applications of sequences to single outputs, single inputs to sequences, and sequences to sequences for all of the tasks that we want to do. In fact, with our sequence to sequence operations, we can do music generation, which is actually what we're going to be doing in the lab associated with this lecture, where you will be able to create a recurrent neural network with TensorFlow and PyTorch to generate your own Irish folk songs. So the design criteria for sequence modeling has several different steps that we need to account for when we want to have accurate sequences. So for our recurrent neural network, we need to be able to handle sequences with different lengths. Remember the long-term dependencies from previous context in the sentence, meaning that at the end of the sentence, we still need to remember important parts of the sentence from the very beginning. And we also need to remember information about the order of the sequence, as especially in many different types of sequences like text, order is very important because when the order is changed, the meaning of the sequence changes as well. Finally, we need to be able to share our used parameters across the entire sequence that we generate and input to the RNN, including the weights and biases. So recurrent neural networks have been designed to meet all of these criteria. And I'm going to be going through several examples to illustrate this. So let's say we have a problem in sequence modeling where we need to predict the next word. So we have a sentence, "This morning I took my cat for a walk." And we want to have the "this morning I took my cat for a" given those words, we want to predict the next word of walk. So we need to now also represent our language to a neural network, as all of these computations will not work on they will not work on characters or words, and they have to be converted to numerical inputs. So this can be done with several different methods, like embedding. So to embed our text, we can first find all of the unique words in our vocabulary, which in our case of our single sentence is every single word in the sentence, and we need to assign each unique word to its very own index, which is the process called indexing, where we assign each word to its index. Then we can use that index to perform different types of embedding. Most commonly, we use a type called one-hot encoding or embedding, where each word is assigned to a vector that is the size of the entire unique vocabulary size, and everything is set to 0 except for the value that is at the index associated with the word. So for our word cat, which has index 2, the number at index 2 is this second one here, which is the ith index, which we set to 1, which is why it's called a one-hot embedding. Additionally, if we want to do something smarter, we can use something called a learned embedding, where we have a two-dimensional or more space where words that are related to each other are mapped. So for example, run and walk are similar, so they will be close in space. Just like dog and cat are both animals, meaning they will also be similar in space, whereas day and dog will be very far apart as they are extremely unrelated. So the second criteria we need to meet is handling variable sequence lengths. So if we have a sequence length of 4, the food was great, we still need to be able to handle much longer sequences, such as we were hungry but cleaned the house before eating, because to predict that next word of eating, we need to be able to remember all of the previous context from the word hungry. Similarly, in the 6-word sentence of we visited a restaurant for lunch, to predict lunch, we need to remember the syntax and context of restaurant. So this means we need to be able to handle variable sequence lengths as well as remember previous context. So this also segues into the long-term dependencies. So let's say we have this extremely long sentence of France is where I grew up, but I now live in Boston. I speak fluent blank. To fill this sentence with the word French, we need to go all the way back to the first word of our sentence, France, so we can accurately predict the next correct word. Additionally, we need to remember the differences in the sequence's order. So for example, if we are commenting on food, the difference between the sentence, the food was good, not bad at all, and the food was bad, not good at all, is very slight, only switching around 2 words. But the sequence meaning is extremely changed, meaning that each sequence's order should be preserved in the model so it understands the dependencies and differences between different sequences and their order. So again, this is all just to illustrate how recurrent neural networks need to match these criteria in order to ensure that they can accurately predict next words or accurately classify different sequences. So again, the criteria are handling variable length sequences, tracking long-term dependencies across a long sequence, maintaining information about the order of a sequence, and sharing the different weights and biases across the entire sequence. So I see a question about where one-hot embeddings would have many different dimensions, and this is actually a very good question, as often when you have a vast data set, your one-hot embeddings will be extremely long. However, as one-hot embeddings only include zeros and ones, they are usually accepted for their high computation and sometimes can be abstracted away altogether, and only the indices are used for each word, where instead of having this one-hot embedding, we use an index. For smaller vocabularies with few unique sequences, we can use one-hot embeddings as they will be small and very efficient, whereas for larger unique word vocabularies, we will need to use indexing or even learned embeddings for higher efficiency. So that was actually a very good question. So now I would like to cover how we can perform the process of computing the gradient and optimizing the weights based on those gradients for something that has different time steps. So this means we now need to compute the gradients and backpropagate through different time steps. So before, the backpropagation algorithm we used was to first map the inputs through the hidden layer to the outputs, and then go backwards or backpropagate by taking the derivative of the loss function with respect to the original inputs to get a value called the gradient, and then shift all of the weights in the direction opposite of the gradient in order to change them to optimize our loss to be the lowest value possible. So now we have our diagram where each individual time step returns its own loss, and all of these losses are summed to achieve our final loss value, evaluating our recurrent neural network. So if we want to go backwards through it, we have to go backwards through each time step to the hidden state, and then go from the very last hidden state all the way back to the first in order to compute our gradient. So let's say, for example, we are at this last time step here. So we go from the loss value to that specific loss value for that hidden state through the output, the hidden layer, and then from the hidden layer to the next time step, the previous one, and then keep passing all of the derivatives and gradients through all of these hidden layers to achieve our gradient value to optimize our model. So we can simplify this diagram by showing that the hidden state is really just taking the derivative from the last hidden state all the way to the first one, which is our standard gradient flow. So computing the gradient for our first hidden state of H0 is extremely complicated and can have many different computations involved. So because of these many computations, we sometimes run into the problem of exploding gradients, where there are many different gradient values greater than 1, and they're all multiplied together to have very large gradient values that are impractical to use for training. So we usually solve this by using a method called gradient clipping to scale down these big gradients to more manageable values. Another problem is sort of the opposite, where we have many gradients less than 1, and when they're all multiplied together, our gradients start to vanish, which we have multiple different methods of solving, including activation function changes, weight initialization changes, and changes of the network architecture. So the problem with these vanishing gradients is because when you multiply all of these small gradients together, the errors that you've previously had in longer contexts have smaller and smaller gradients, and our weights are not optimized correctly to fix those issues. So for example, if we have the sentence, the clouds are in the blank, and we want to compute the gradient so we can predict the next word, it would not be that bad, as there is not that much distance between the output and our given inputs from the beginning. However, if we have our long sentence, such as I grew up in France and I now live in Boston, I speak fluent blank, this will lead to much more problems, as there is a far longer dependency, and if our gradients are vanishing from the beginning till the end will not be able to account for the previous context, so we will not correctly predict the next word. There have been several solutions to fix this, but now more recently, we use a method called gating mechanisms. So these gating mechanisms use different gated cells where our neural network layers are sent through a mathematical operation that only takes certain parts of information through the cell to be continued on. And usually that information is the most important parts. So through this gating mechanism, we have been able to create modified recurrent neural network architectures such as long short-term memory networks, which use these gated cells to take all of the time steps and extract the most important information from each. We will actually be using a long short-term memory model in the lab associated with this lecture for our music generation. So now that we understand recurrent neural networks at a deep level, I would like to cover their different applications as well as their limitations. So, for example, in the lab, we are going to be doing music generation, where we're going to have an input sequence of given music, and we need to be able to output new characters predicting the next character to generate new music. So as an auditory example to illustrate how this would work, I actually went through this lab myself and optimized the parameters in order to generate some music. So I'm going to let everybody listen to the first few seconds to see how it works. And it continues on for about another 2 minutes, but that illustrates the power of these recurrent neural networks to generate new music pieces that have never been seen before based on simple input data of previous music. So another task that we can use is sentiment classification, where we take a given input sequence of words and we run it through our recurrent neural network to achieve a final output of a given sentiment of the sentence. So for example, if we have a sequence of I love this class, then the sentiment is positive based on the love and the exclamation mark at the end. So for this example, we could use a cross entropy loss as we are predicting a probability of the sentiment being positive. And if it is greater than 0.5, it is positive, less than 0.5, it is negative. So for example, if we want to classify the sentiment of tweets, we could classify it as positive or negative based on the sequence that is inputted to our recurrent neural network. So there are these different applications of neural networks, and they seem to work very well. However, they occasionally have limitations. So with all of our different sequences, there can sometimes be a bottleneck in the different encodings that we may have, as passing all of the encodings for each sequence can be difficult between each recurrent cell, and they can sometimes get lost till the end. Additionally, since the architecture of the recurrent neural network is built to rely on each previous cell, we are not going to be able to parallelize these operations and make their operations faster through graphical processing units or GPUs. Finally, they usually don't have a long memory when they are in their default orientation of recurrent neural networks, which is solved by the long short-term memory architectures or others, but with our default recurrent neural networks, they usually do not have a very long memory from previous contexts. So currently, we have this architecture where each recurrent cell has an input mapped through several computations to an output, and each hidden layer is passed to the next in order to achieve our final output. So we have all of our limitations, and we want to have a continuous stream of outputs, meaning that instead of predicting new sequence piece by piece, we have it as all in one go. Additionally, we want to be able to parallelize our operations so that way they can be much faster computed. And finally, we want to have a longer memory to retain all of the previous information from our sequence. So let's say we don't have recurrence at all, and the entire sequence is provided at once through the hidden layers all at once to achieve our final output. This seems like it would achieve our desired capabilities, but in reality, although we have no recurrence, this method is not scalable, as the more longer sequence you have, the computations will be exponentially more computationally intensive. Furthermore, we do not retain any order about our sequence, as it is all sent together at once, and the order may sometimes be confused depending on how it is inputted. Finally, we no longer have a long memory at all, as the entire sequence is inputted at once, and there is not really a memory altogether, since it's only one input, and there is no need for memory of previous inputs. So we came up with another idea to identify and attend to what's important in a given sequence. And this concept is called attention. It has been developed in the past few years and is used in many different novel architectures such as GPTs or generative pre-trained transformers. So if you have heard of ChatGPT or any kind of GPT before, you can comment in the chat, and hopefully everybody has, as is a very up and coming technology that has been having a lot of press appearance as well as much more attention in general. The concept of self-attention is where instead of scanning each pixel in a given image one by one, we can immediately identify the important parts of our image. This would work for other sequences as well by inspecting the given sequence that it has and looking at what parts will be most important. So instead of looking at each part of the sequence one by one and identifying which parts are important, we as humans can quickly look at an image and identify the most important part. So for example, in an image of Iron Man zooming past buildings, we can immediately identify Iron Man as the most important part of the image, as he is in the foreground and is having a lot more light compared to the background. So usually, we are going to be able to do this by identifying which parts we want to attend to and then extracting those features that have the highest attention. So let's say, to help you with this course, you want to perform a search to learn more about neural networks. So you go to YouTube and search deep learning. So this is going to be called your query. And for every key in the YouTube database, we're going to compare the query to the key to see how similar each one is. So if we have a 12-hour video of sea turtles and coral reefs, that is not that similar to our query, as although it may be deep ocean or something like that, it is not deep learning in the type that you want to help you with this course. Second, let's say we have a video of the lecture from 2020, the Introduction to Deep Learning from the MIT Intro to Deep Learning course. Deep learning is mentioned several times in the title and in the description, so deep learning would most definitely be something that matches this key. Finally, for our third key, the Kobe Bryant fadeaway shot, it could be related to learning if you want to learn how to do it, but it is not deep learning for the architectures and neural networks that you want. So out of our three keys, only the second key of Introduction to Deep Learning is the most pertinent. So this computation of comparing each query to each key is called computing the attention mask. And then we can use the attention mask to find the values, the keys with the highest attention, and then extract their values, which in this case would be the video itself, the description, the author, and much more. And then we return those values as the most pertinent. So now let's look at a more concrete example of how this would work. So let's say we have an input of a sequence, he tossed the tennis ball to serve. So first, we need to encode the position information in this sequence so we can understand the parts of each and where they're located in the sequence. Since all of this data is fed in at once, we need to make sure we understand each part's position. So we have our embedding for each part of the sequence. We add position information to each embedding, and now we have our position-aware encoding, where each part of the sequence is encoded with its position. Next, we need to get the query key and value for each part of our sequence, which we do by multiplying it by different linear layers to get a query output, a key output, and a value output. Then we need to take each query and each key to compute the attention score, which is the difference between both, which we do by having a dot product between the two query and key, and then using a scaling value to put it between 0 or 1. So this process is called cosine similarity or the similarity metric, and we can do this for every query and key to get a attention weighting. So this will look like a box that maps each part of the sequence to the rest. So we can see that in this example of he tossed the tennis ball to serve, the words that are exactly the same are in deep red as they're most related to each other, whereas the lighter pink words such as tossed and to are extremely unrelated, making them light pink. Words that are somewhat related, such as tennis and ball, are going to have a somewhat in-between color of pink, of deep pink, because they are somewhat related but not exactly the same. So we find this by computing a value called the softmax of our attention score. So that way we can put it between a probability value of 0 to 1 and put them all in this sort of table format. So this would mathematically be represented as a matrix, and we can multiply this attention weighting by every value that we have to get a final output with the most important features. So we can extract the ones with high attention and pertain and work with those first to find the most important parts of every sequence we work with. So now in a more mathematical architecture that we can visualize, we take our position encodings, put each one through a linear layer to get our query, key, and value, and then we take our query and key through matrix multiplication, a scaling, and softmax operation in order to achieve probabilities and a attention weighting matrix that we multiply by each value with matrix multiplication to get our output with the most pertinent and most high attention values. So this is extremely important as these attention nodes can be turned into attention heads, and all attention heads can be combined as the building block for the transformer architecture. So the transformer is the T in GPT or ChatGPT, which is why these models are so impressive, as this transformer architecture is one of the most state-of-the-art at the time of this course. So with this transformer architecture, we can now perform many novel different tasks, such as ChatGPT to answer all of your questions that you may have. So if we want to apply multiple self-attention heads to our example of Iron Man through the city, we can take our attention weighting for our first head, multiply it by the value to get our output of Iron Man. But the beauty of this is that we can take multiple different self-attention heads. And for the first attention head, we have Iron Man, but in the second head, we have the building on the side, and in the third head, we can have the small machine that is chasing him. So attention can be applied in many different fields, especially like language processing. So as I've been saying, ChatGPT and GPT are based on these attention heads, and they allow us to understand sequences such as text, images, and video. And as part 2 of this course is going to be covering the large language models and transformer architecture, so be sure to look for more updates coming soon on that part of the course when the schedule is released. Furthermore, we can apply attention to biological sequences, which has allowed us to create protein structure models that can design new proteins to be used in the human body to even help medical diagnosis or even cure diseases. Finally, in computer vision, models called vision transformers have been created to actually do the example of what we previously showed with Iron Man to find pertinent parts of an image, extract them, and perform many different tasks that allow us to do everything we can do today. So in conclusion, we covered recurrent neural networks and what makes them extremely useful for different sequence modeling tasks, and we showed that how they model sequences is through a recurrence relation where each time step in a given sequence is chained to the previous one by taking its state and sending it throughout the recurrent neural network. Then we saw how we can train recurrent neural networks to have higher accuracy by using backpropagation through the different time steps. We saw how we can have these recurrent neural networks be done for music generation, classification tasks, machine translation, and so much more. Then we looked at the limitations of recurrent neural networks and found that self-attention can be used to solve these limitations by modeling sequence without recurrence, but pertaining to the most important parts of a sequence and allowing us to perform much more complex tasks than we could previously without the transformer architecture and attention heads. Now, I would also like to note that self-attention and the transformer architecture is the basis for many large language models, or LLMs, which are similar to the GPTs that you see today, like ChatGPT, and open source models such as Llama offered by Meta, and Mistral, offered by the Mistral French company, which allow us to ask questions, provide images, videos, text, and receive answers to any question we may have, which makes self-attention very important. So we're also going to be covering large language models and the transformer architecture in part 2 of the course, so be sure to stay tuned for that.